This is number 9 from the 2015 National Chemistry Olympiad test. I'm going to go through this problem and a few others to give you a kind of a head start on getting ready for these. Alright, so here we have a titration. It's with sodium thiosulfate against an iodate solution mixed in potassium iodide and HCl. So our two reactions that are going on. So in the iodate-iodide mixture, what's going to happen with these two things is that they're going to turn into the I3- ion. And that is then going to get titrated with the thiosulfate to form this and some iodide. So probably looking at a starch indicator and looking for the endpoint when it goes from blue to clear. And they want to know which of the following mistakes will lead to a value of the thiosulfate being checked against this that is higher than the true value. And so if we look at the four different situations here, in part A, the student overshoots the endpoint of the titration, meaning that they add more of this than they should have before realizing they've reached the endpoint. Okay? So they've added too much of this, and they know the amount of this. So what's going to happen there is they're going to think that this solution is more dilute by virtue of the fact that they've added too much thiosulfate. So when they see that go clear, they're thinking that they just had it go clear, but really it would have been clear a little bit before then. So they're going to, they're going to actually do the opposite of this. They're going to find that the value is lower than the true value because they're going to underestimate the concentration of it. So A is not correct. So and then in B, the sodium iodate solution is contaminated with NaCl. And so we're then looking at a chloride mixed with iodate. And the problem with that is that potentially the chloride could react with either one of these, reducing its amount. So either the chloride and the iodate could then form, hypoiodite or iodine and chlorine, or it could add extra chemical to this that's going to react with this. And so lots of different reactions that could go wrong there. So let's table this one for now. That's a possibility. The next one is the Ki and HCl solution is allowed to stand overnight. And there we're looking at iodide mixed with chloride. And neither one of those is going to react with one another because they're both completely reduced. And so this is not going to cause anything to change. And then the last question, so we're really down to B and D here. The last question for the sodium thiosulfate pentahydrate, what I read this to say is that they get their mass of the pentahydrate, and then before they make the solution, some of the water leaves. And since they've already recorded the mass and they're not losing anything except for water, the fact that they're going to later make the solution makes that water leaving irrelevant. So then D is not going to be the answer. So in that case, we can go back and B would be our best choice, and we'll go ahead and pick that. Here we have something that could eventually either reduce the amount of this or increase the need for this. And so that's going to, both of those will lead to a value of the molarity being higher than the true value, and so B is our answer. Okay, number 11, elemental silicon is oxidized by oxygen. So our first reaction is we're just going to form silicon dioxide. That gives a compound which dissolves in molten sodium carbonate. So silicon oxide plus sodium carbonate actually forms what's called sodium silicate. And CO2 gas. Okay? Then that solution is treated with aqueous hydrochloric acid or precipitate forms. So we're going to add hydrochloric acid to this. When we add hydrochloric acid to this, that's going to turn this back into silicon dioxide, sodium chloride, and water. And it says a precipitate forms. What is the precipitate? So our precipitate's going to be the silicon dioxide right there. So we form silica gel. Okay. All right, and the metal dissolves in 3 molar sodium hydroxide solution with the evolution of a gas to form a clear, colorless solution. Upon neutralization, the solution forms a gelatinous precipitate. So this to me screams aluminum, and the specific reactions that are going on there. So aluminum has a thin coating of aluminum oxide. So that plus the hydroxide is going to dissolve away that protective coating that we have. okay? So only in high pH will this work. And hence the term 3 molar, so we're looking at a concentrated solution. Then, after that, the aluminum is going to react with the hydroxide itself. And this is going to be a redox reaction when we form a complex ion. And so, let's get the full thing out here. So we're going to end up forming 2 aluminum hydroxide, tetrahydroxa complex ions, and then hydrogen gas. So this is our gas being produced. So this is a complex ion, and therefore it's a colorless solution. And it's colorless because, of course, the aluminum does not have that d orbital splitting. And then when we neutralize it, it forms a precipitate. So what's happening there is that when we add acid to this, if we add just the right amount, we're going to end up with the aluminum hydroxide insoluble precipitate. Okay. So that's the particular reaction that's going on there. And this is part of course, the extraction of aluminum ions from bauxite. And so that's why this is a good question. All right, which of the following substances experiences London dispersion forces? So anything with electrons is going to experience London dispersion forces. So even though this has hydrogen bonding capabilities and dipole capabilities, this is also going to have dispersion forces because you're still going to get those temporary dipoles formed. So they're not the strongest force available, but they are going to be present. So the answer here would be C, both 1 and 2. All right, number 17, we're given a phase diagram, and we're asked which statement is correct. So in statement A, it talks about the solid having a greater density than the liquid, and I believe this is actually going to be our answer. But what that's referring to is it's referring to the line here between the solid and the liquid phases. And so between the solid and liquid phases, you can have one of 2 things. You can have a line that goes like this, or you can have a line that goes slightly backwards. And water is the classic case of that. So in water, what happens is when you have the solid and you increase the pressure going up, you form the liquid. And that's because the liquid has a greater density. And so when you put a lot of pressure on it, it kind of collapses it into that state where things are closer together. Versus here in the blue, if we have a liquid and we increase the pressure, then we turn into the solid. And that indicates that the solid is more dense than the liquid. That's the case we have here. We can see it from the slope of the line that as I increase the pressure, then I'm going to go from the liquid to solid. So A is our answer. Let's go through the other ones just to make sure. Solid methanol sublimes at atmospheric pressure. Atmospheric pressure, we are above the triple point, and so therefore we'd have to be below that triple point to go for a sublimation. So this is false. Solid, liquid, and gas can only exist at pressures above 1 atmosphere. That's not true. We have the 3 here at this point here below 1 atmosphere, so that's also false. And then 200 degrees and 1 atmosphere pressure, methanol is a supercritical fluid. So we're looking somewhere around here. So in order to be a supercritical fluid, we want to be in this region here, where your vapor and liquid kind of coexist in one phase. So our supercritical fluid, that's not at that particular point here. We're outside that range. So A is indeed our answer to that one. That's a common question here where you're looking at the slope of the solid liquid kind of barrier. So anytime you see that, there's a high likelihood of that actually being a choice. All right, next question, number 18. What statement about atoms arranged in a body-centered cubic crystal is correct? So in a body-centered cubic crystal, we have our cube. We've got 8 atoms, 1 at each corner. Okay, so each of those corners counts towards 1/8 of that atom, counting towards this particular unit cell, and then 1/8 counts towards the other 7 that are adjacent to this unit cell. And so we count 1 atom there from those 8, and then we have 1 that's in the center of the whole thing, which is just belonging to the 1 unit cell. So we have 2 atoms present, total in this body-centered cubic. And then additionally, this one atom in the center is going to touch each of those corners. And so we have a coordination number of 8. So if we go through and look at our choices here, it's not observed as the structure of any metallic elements. That's false. There are not many, but there are some. It's also called a cubic closed pact. That is a name that means the same thing as face-centered cubic closed pact, and there's hexagonal closed pact as well. And then the unit cell contains 2 atoms. That's our correct answer. And then each atom has 6 nearest neighbors. That's the coordination number. This is true for simple cubic, has 6. Body-centered cubic has 8. Face-centered cubic and hexagonal closed pact, those each have 12. So this is wrong. So our answer is C. Okay. All right, 24. This is a very common thing to be asked on a Chem Olympiad. It's a very challenging question. The theory here is that if you have, I'm sorry, I'm going a question ahead. So never mind. All right, so this gives us an equilibrium constant of 10 to the minus 5th at a certain temperature. And then it says the equilibrium constant gets bigger as temperature goes up. So K increases as temperature increases. So we're looking at thermodynamic information, enthalpy and entropy. So the first thing I would state is we know delta G is positive at standard temperature because our K is less than 1. Okay? So that's what we know. And then we also know that delta G naught becomes more negative as temperature rises, because if K is going up, that means that our delta G value is becoming more negative. And so maybe we don't even reach 0 at until we're really high temperature, but we know this is becoming a smaller and smaller positive value. So what we can do then is we can look at the equation for this and kind of do a little analysis. So in order for delta G to be positive, either delta H has to be positive, delta S has to be negative, or both. Okay? But also, for it to become more negative as temperature goes up. So as temperature goes up, if delta G is more negative, that means delta S must be positive. Which means that in order for delta G to ever be positive, delta H must be positive. Because as temperature rises, this factor is going to become larger. So we're looking at both being positive, and therefore we will go for A as our answer. Okay, so here's 26. Here we have a kinetics one. We're looking at second order. So what you want to do for this, there's 2 ways to solve this. One is to use your full out integrated rate law, just like this. So what we can do here is we can do a calculation where we plug in a bunch of values. So our initial concentration is 1 molar, and it takes 0.5 hours to decrease to 0.5 molar. So we have a final concentration of 0.5 is equal to K times time, which is 0.5 hours, plus 1 over our initial concentration of 1. So we're looking at 2 equal to 0.5 K plus 1. So then 1 is equal to 0.5 K. So K is equal to 2. Hours to the minus 1. Right, and it would be polarity to the minus 1. So what we can then do is that we can now plug in our new information. How long will it take for a solution of X to decrease from 1 to 0.25? So then we're looking at 0.25 as our final, equal to K, which is 2 times time, plus 1 over the initial 1. So we're looking at 4 is equal to 2T plus 1. So we get 3 is equal to 2T. So time is 1.5 hours. Which would be C. Alternatively, other way to do this is you can go through and you can do this with half-lives. So the half-life from the integrated rate law is equal to 1 over K times A naught. So what we can do here is we figure out that since K is constant and is not going to change, we can go ahead and figure out that initially we're at the 1 molar state. So we know that it takes 0.5 hours if our initial concentration is 1. Okay, so we can solve here that K is going to be equal to 2, just like we saw last time. And then what we can do is we can say, okay, well so we get our first half-life, and that takes us down to 0.5 molar. Now we need to cut it in half one more time. We need a second half-life. So now we've got 1/2 times the initial concentration of 0.5. So our new half-life is 2 times 0.5 all divided into 1. This is 1. So our new half-life is 1 hour. So it takes a half hour to drop the first amount, and it takes an hour to drop the second amount. And so total it takes 1.5 hours. Either one of those situations will get you at the same answer. And one of the ideas here is that as your concentration is decreasing, it's taking longer for the reaction to happen because you're in a second order reaction where the increased concentration has a squared effect on your rate. All right, 35 is the one I was looking for a couple questions ago. This is a common question, very difficult. What we're going to do here is we're going to effectively combine two reactions. So our reaction is the silver chloride solid turning into silver ions and chloride ions in solution. So that has our KSP value. And we have a second equation, which is the formation of the silver, just one of those, ammonia complex. So what we want to know is we want to know what the combination of both of those reactions is. Now when we add these two together, the silver ions are going to cancel. We're going to be left with this, the silver chloride dissolving ammonia. This. So we want to know what the K of that is so we can do some analysis. Okay? So it turns out that if you can add two reactions up to form a new one, that the product of their equilibrium constants will be equal to the new equilibrium constant. So if we multiply KSP times KF, we get our equilibrium constant. So the product of those two is 0.018. Okay? And then we know that at equilibrium, this is going to be equal to the following. It's going to be equal to the concentration of the complex ion times the concentration of chloride divided by the concentration of ammonia squared. And we're going to leave the solid silver chloride out of that calculation. So if we want to dissolve 0.01 moles of AgCl, then we can look and say, okay, well that's going to mean that we're going to need to have 0.01 molar of this and 0.01 molar of that. So what we get is 0.018 is equal to 0.01 squared over the ammonia squared. Okay, so when we solve for this ammonia, it turns out to be 0.075 molar. So it's gonna be 0.075 moles. However, that's at equilibrium. So if we think of this in terms of an ice chart, the value I just got was the equilibrium value. I want to know now what would the initial value be. And so for every 0.01 of this that reacts, it requires 0.02 moles of that. And so our actual initial value is equal to 0.095 moles or 0.095 molar. And so therefore C is our answer to 35. All right, and I believe this is our last one here. So 36, we have a 100 milliliter solution of a weak monoprotic acid titrated with 0.5 molar NaOH. We get this curve, which the statement is not true. So phenolphthalein as a suitable indicator, we would need our phenolphthalein is going to change at a pH of 9. That's even a little high right there that I've drawn on there. So that's fine. That's along the equivalence point. So this would be correct. This is fine. A buffer solution is formed when 15 milliliter of NaOH is added. That's also fine. Anywhere when our amount of NaOH is more than 0 and less than 20 milliliters. So anywhere from here to here, essentially, that's a buffer region. Now it's a better buffer region the closer we are to 10, but that technically has some conjugate base or some weak acid and some conjugate base present. Okay, pK of the acid is 4, so our pK value, we're looking somewhere over here, trace that back. It looks like it's about 3, which is close. So this might be wrong, but let's check the last one first to make sure. And then we'll come back and evaluate whether or not we think that that's close enough or not. So the initial concentration of the acid is 0.1 molar. So to do that figuring, we're going to go here. It takes 20 milliliters of base, which is 0.5 molar. And so that should be equal to the moles of the acid. In the acid, we have 100 milliliters to start with. So if we go ahead and do this out, we're going to have 20 times 0.5, that's 10, divided by 100. So the molarity of our acid is equal to 0.1 molar. And that's the initial concentration. So this is also correct. You can't figure that out from the initial pH because we don't know the Ka, but we can figure it out from moles, which means that C would therefore be our answer.